I looked at the general idea of applying Newton's second law, and now I want to do the same thing with just some examples. So this is applying Newton's second law. An example. The situation that I would like to look at is a block that's on a ramp. We're going to give this ramp an incline angle here. Let's go 30 degrees. And we'll give the block a mass of 5 kilograms. We have not gotten into any friction or anything like that, so this is just going to move pretty freely. We want to know what's the acceleration down the ramp. So and let's find the contact force with the ramp. Okay, first, free body diagram. Here is the box. There is the angle of the ramp. I'm going to have mg down, and I'm going to have a normal force that's out this way. It's out that way because it has to be perpendicular to my ramp. That's really it. Now, my motion in this problem is going to be along the ramp, so I would like to make along the ramp be my x-axis. And then that means that this has to be my y-axis, because it's perpendicular to x. And I have a free body diagram. And I said my mass was 5 kilograms, and my angle here is 30 degrees. Okay, the first thing that I want to do is break my vectors into components as much as I need to. Now, looking at this thing, before I drew on my axis, I would have said that my normal force is diagonal and my mg force is straight down. So it seems like a logical thing that it's going to be that normal force that's going to have to break into components. But I took a second and thought about it and said, man, all my motion is going to be down this ramp. So that makes a lot more sense to use that as an x-axis. That means now that my normal force points just in the y direction, but my mg force points diagonally. If you are having trouble seeing that, tilt your head about 30 degrees to the right. Normal force goes straight up and down. The gravity force is diagonal. So that's actually the one that I'm going to have to break into components. I'm going to break gravity into two components. I've got one that goes this way, that is along my y-axis, and one that goes this way along my x-axis, right? This along x, this along y, but it's negative y. And that makes a right triangle. So if I call this thing my gravity x and this thing my gravity y, I'm going to need to be able to find those. Here's where we start to mess around with triangles a little bit. It won't be bad, and I'm going to erase it afterwards. I have right here a right triangle. There is a 30-degree angle there, theta, which means this angle up here must be 60 degrees. It's what's left over from 90. Now from the ramp to the y direction, that whole thing is 90 degrees, so this little angle plus this piece has to be 90, which means this piece in here is going to have to be theta, 30 degrees again. I'm going to get rid of that stuff because, no I'm not, I'm going to leave it. This one has to be 30 degrees. mg is, so now I'm looking at this triangle, mg is the hypotenuse, which means mg is the vector that I have to break into components. This gx is just going to be an mg times the sine of 30 degrees, because it's the opposite to the angle, and gy is going to be an mg cosine 30 degrees. And now I do have all of everything I need. In the x direction, I'm going to write my sum of forces equation. Sum of forces equals, I'm going to take my positive x, so that's that gx, and I don't have anything else pointing horizontally, like along x, so that's it. That's my sum of forces. Sum of forces is always going to be equal to mass times acceleration. And that is an acceleration in the x direction. I know gx, right? If I put in my details here, mg sine theta equals m times ax. I could divide by m, but I don't even need to because it cancels. And I get that my acceleration in the x direction is just equal to g sine theta. (10 meters per second squared) times the sine of 30 degrees. The sine of 30 degrees happens to be a half. So I'm going to get an acceleration down the ramp of 5 meters per second squared. Second part, I was asked to find the contact force between the block and the ramp. The contact force between the block and the ramp is this normal force. So now I'm looking in the y direction. My sum of forces in the y direction looks like this. I've got this normal force going in positive y. I have gy going in the negative y direction. And that equals mass times acceleration in the y direction. In the y direction means perpendicular to the ramp. If I have a negative acceleration in the y direction, that means my block is sinking into the ramp, right? I would be accelerating this way, and that doesn't make sense. If I have a positive y acceleration, that means my block is now levitating off of the ramp. Also no good. In the y direction, my acceleration is going to be 0. That lets me solve. My normal force is equal to gy, and gy I said was mg cos 30. So I'm going to get 5 kilograms, 10 meters per second squared, times the cosine of 30 degrees. Cosine of 30 degrees is 0.866 times 50 is going to be 43.3 newtons. That is my normal force, which is that contact force. And that's the whole problem. I treated my x and y directions separately and just applied Newton's second law for both. The second part of it, that y direction, looked a lot like a translational equilibrium because in that y direction I am in equilibrium, and I should be. Otherwise I'm moving off the surface or into the surface of the ramp, and that's not what's going on. I'm just going to slide down the ramp, no big deal. The translational equilibrium case, we can approach it exactly the same way with this Newton's second law setup. Like, we don't even have to anticipate that ahead of time. I was able to just set this equal to mass times acceleration. It's just I had to recognize afterwards my acceleration in that direction is 0, and that condensed it back down into that translational equilibrium sort of problem. If I've got this same problem, and instead of doing this, maybe I am pushing the ramp, or pushing the box up the ramp, then I would have to add an extra force here. I'm going to draw it in blue just so that you can see that it's separate. It's not going to affect my y direction at all. I'm just going to have here minus push. We're going to actually do that problem. I've got this same setup, and now I'm going to ask a different question. What minimum force do I need to apply to push the box up the ramp? So I set up my same equations that I had before, and I'm really only worried about the x direction. The y direction, there's not much going on. I'm not finding anything new. So my sum of forces I've got mg going downward. I've got a normal force going this way. And I've got this push force going up the ramp. I have set my axis up this way. Here is y. Here is x. I guess if I'm going to try pushing this thing up the ramp, maybe I'll make this be my positive x direction over here. And I know in here was my 30-degree angle. I'm going to again have to break up my gravity. There's my gy, which I'm not really going to end up caring about. There's my gx. And just like before, the angle of my ramp will end up being the angle inside this triangle. So my gx is going to be an mg sine theta. My sum of forces in the x direction. That's how I got into this mess in the first place. Is I've got that push force going up the ramp. That's what I'm solving for. I've got mg sine theta going down the ramp. And that equals mass times acceleration in the x direction. Alright, what do I need for a minimum force? If I can get an acceleration of 0, then this box is not going anywhere. If I get an acceleration that's positive, then the box starts moving up the ramp. An acceleration that's negative, the box is going to start sliding down the ramp. So what I want to do is find my cutoff. I want to set this thing equal to 0 and solve this. And say I get a push force of whatever, 100 newtons. 100 newtons to get this thing to be equal to 0. That means if I push with 100 newtons, this thing's going to stay still. If I push with 100 newtons plus a breath, then this thing starts moving. And that's how we solve these problems, really, is we say, let's find the threshold value, and that's the minimum force. So I'm going to solve this thing. I've got push force minus mg sine theta equals 0. My push force is equal to mg sine theta. If you like, what it really is this has to be greater than instead of equal to, right? Any positive number will work. So maybe I'll write it that way. I won't. You're going to always see it as an equal sign. Mg sine theta, so I've got 5 kilograms, 10 meters per second squared, times the sine of 30 degrees, which happens to be a half times 50 that is 25 newtons. I need to push this thing with at least 25 newtons to be able to get it to move up the ramp.